Okay, so we're going to start by doing some optimization problems here. These are problems where you're trying to find a function that you're trying to find the maximum or minimum of that function so that you can find a maximum or minimum related to some word problem. So the first problem we're going to do is number 3 here. So number 3 is a farmer has 600 meters of fence and wants to enclose a rectangular field beside a river. Determine the dimensions of the fenced field in which the maximum area is enclosed. Fencing is required only on 3 sides, those that aren't next to the river. Okay, so you're given 600 meters of fence and you want to find the dimensions of the field that give you the maximum area enclosed. So that thing that you want to maximize is the area. So we need a formula for that. And so let's look at that. So the area is going to be length times width. Okay, so if we've got this as our area that's going to be fenced in, and it's next to a river, so here's the river. So you only need these 2 sides and this one. Okay, so area is going to be x times y. That has 2 variables in it. We can't do calculus with 2 variables right now, so we need to somehow reduce that to 1 variable. And the way we do that is by using the other information that we're given, which is we have 600 meters of fence. So from that, we can have some relationship between x and y. So 2x plus y equals 600 meters. And therefore, y equals 600 minus 2x. Okay, so that is the equation that's called the constraint. Okay, constraint. So that is the one that relates the 2 variables in the equation that we want to maximize or minimize. That's if there are 2 variables. If there aren't 2 variables, then we're good. If there's more than 2 variables, then we've got to come up with more relationships. Okay. So that's the first thing you want to do, is find the relationship of the constraint after you've got the equation that you want to maximize or minimize. Once you've got that y equals 600 minus 2x, you can substitute it in. And now you have a function where x is the variable, and this is it. This is a quadratic. This is one you know how to solve without calculus. You could graph this. It's a quadratic that opens down. Okay, so if you multiplied that in, you'd get this. Then you could have left it in this form, found the zeros of it, so x equals 0 and x equals 300. The maximum is going to be at then 150. Okay, but we want to use calculus and come up with the same answer. So a prime of x equals this. And we know that the slope of the tangent is 0 at a maximum or minimum, okay, of a continuous differentiable function. So let's set the derivative equal to 0, and you get a prime of x equals 0. Which means 4x equals 600. So put a 0 here, rearrange this, and you get 4x equals 600. Okay, divide by 4 and you get x equal to 150, which is what I said earlier. So we use calculus. It was not necessary to use calculus here, but it's going to be for future problems, so that's why we're doing this. Okay, so the dimensions are then going to be x equals 150 meters, and y is 600 minus 2 x's, which would be 300. So the dimensions are 150 by 300 meters. Okay, so that's how you figure out that problem. The next one we're going to look at is page 145, number 8. Okay, so page 145, number 8. For this one, okay, so a net enclosure for practicing golf shots is open in one end and find the dimensions that will minimize the amount of netting needed and given the volume is 144 meters squared. Okay, so netting is only required on the sides, the top, and far end. Okay, so this is as if there's no netting on the bottom here, and there's no netting on this end. It's just these three sides here and one end. Okay, so you want to minimize the amount of netting. So you want to actually minimize part of the surface area of that prism. Okay, so let's take a look at this. Okay. So the volume is now the constraint. The volume equals x squared y. Because it's a square end, okay, so you know this is the same as this, is the same as this, is the same as this. Okay, so this is called the net if you've unwrapped the diagram there. So if you unwrap that into the pieces that are actually going to be covered in net, then this is called the net diagram. Okay, so those are the pieces that they would need for the netting. So this is x by x, and these three are all x by y. But the volume is going to be x, so length times width times height, which is x squared y. Volume is 144, and you can relate these two variables by saying y equals 144 over x squared. Or you could say x squared equals 144 over y. Whatever is most convenient. Okay, so the area, the surface area that we're looking at is going to be 3xy, so 3 of these, plus x times x, which is x squared. So that's the thing we want to maximize or minimize, but we then need to sub in this expression for x, so we're down to one variable. Okay, so now we have a of x is 3x times 144 over x squared plus x squared. 432 over x, because that reduces, and plus x squared. Now we're going to take the derivative so that we can set it to 0. Okay, so we take the derivative of that, set it to 0, and play around with it so we get to solve this so that we got x cubed equals 216. Now we can just take the cube root of 216, which gives you 6, or you could bring the 216 over and factor that difference of cubes to x minus 6 times a quadratic that's not factorable. Okay, so we know a cubic's only going to give one positive answer. Okay, and then we can sub that in to get y, and from that now we've got the dimensions are 6 by 6 by 4. Okay, so that's number 3. Next one I want to look at, which is a typical problem, is the open top box question. Okay, so the open top box, we're going to look at number 4 for this one. So number 4, I'll go backwards a little bit here. Say number 4, a rectangular piece of cardboard 100 centimeters by 40 centimeters is going to be used to make a rectangular box with an open top by cutting congruent squares, so meaning the same squares, from the corners. Calculate the dimensions to 1 decimal place for a box with the largest volume. So the volume you want to maximize, because that's what they want, the largest volume. And the constraint is the piece of material that they're cutting it from, so the piece of cardboard that they're cutting it from, which is 100 centimeters by 40 centimeters. Okay, let's take a look at this. So we've got this diagram here. So there's the piece of cardboard. It's 40 centimeters along here and 100 centimeters along there. We're cutting out congruent squares from the corners so that you can fold the sides up and create this open top box. Okay, so because we're cutting out these congruent squares, we're letting the dimensions be x and x. That makes this side here 40 minus 2x. So 40 minus x is 40 minus 2x. And then 100 minus 2x is this side. So when we put that together to make the box, we've got these dimensions. The height is x, okay? The length is 100 minus 2x, and the width is 40 minus 2x. Because of this side here, we cannot take squares out that are bigger than half this width here. So the size of x has to be limited to between 0 and 20. So that's where we have this restriction. Okay. So the volume, length times width times height. There we go, x times 40 minus 2x times 100 minus 2x. Okay, expand that out. We get this nice polynomial. And then we take the derivative of that, set it to 0 to find where it has a maximum or minimum. Okay, it's a cubic, so we know it's going to have a maximum and a minimum, possibly, but don't know where. Okay. So when we look at this, v primed equal to 0, we solve that quadratic using the quadratic formula or factoring, whatever you can, to get these two answers, 37.9 and 8.8. Well, 37.9 is outside our restriction of 0 to 20, so that can't be it. So 8.8 must be our answer. If we look at this cubic, okay, for the volume, it's a cubic. It has a positive leading coefficient, so the cubic's shape is going to look like this here. So because it's a positive leading coefficient, it's going to open up on the right. It's going to have a minimum first and then a maximum. So the lower value is going to give us the maximum on this. Okay, so we know that from cubic functions that we know. So 37.8 would be at a minimum, 8.8 would be at a maximum. So the dimensions then are 8.8, and sub them in for the length and the width. So sub in the x for the length and the width, and you get 22.4, and 82.4 is the other dimension. Okay. And that's it for those three questions, and I'm going to post some more solutions as well. I'm probably just not going to talk them through as much.